Professor Manoj Kumar Patel, you are welcome to do your presentation, please.
Yeah, thank you very much. Am I audible?
Yes.
Yeah, okay. Now let us start to share my screen here. Yeah, is it visualized?
Yes. Could you please share your screen in full screen?
Yeah, this is full.
Okay.
Okay. So first of all, I would like to thank to the organizer for providing me the opportunity to talk about the characterization of FI semi-injective module in the webinar studied on scientific development in geometry, algebra, and applied mathematics. So motivation of this work comes from 1995 when Nicholson and Yusuf studied the structure of principally injective ring as if every homomorphism from a principal right ideal to R is a left multiplication by an element of R. After that, in 1999, San and his collaborator extend this notion to module and generalize the idea of principal injectivity to M principal injectivity of a given right or modulium, any modulium. So here, before come to the these are outlines. Here we have to consider definition and examples of the FI semi-injective modules. And next section is characterization and properties. And after that is references. So here before going to define the FI semi-injective module, it needs some basic notion like M cyclic submodule. Here injectivity is defined is map is extended from the submodules of M. Now in that case, in FI semi-injective module, our map is extended, means any map from M cyclic submodule extended from M to M. So for defining what is the M cyclic submodule. A submodule N of M is called M cyclic if it is homomorphic image of some endomorphism of M. Or we can say equivalently, it is isomorphic to M modulo L for some submodule L of M. For example, we can consider every submodule of Z is the Z cyclic submodule, and also we can consider every direct summand of a module M is M cyclic submodule. Also, we can use the terms fully invariant. So a submodule K of M is called fully invariant if it is invariant under all the endomorphism of M. So for example, 0 and M is the trivial example of the fully invariant submodules of any module M. And some distinguished example of the fully invariant submodule is like Sokal. Sokal of M is defined like sum of all the simple submodule of M. And next one is the radical is defined like intersection of all the maximal submodule of M. And next one is the torsion submodule is defined as collection of all the element of M which is annihilated by some positive integer M. And next one is considered the singular submodule is the collection of all those elements of M whose annihilator is a essential ideal of R, or we can consider is an essential submodule of R over itself. So here we look in the diagram here. First we have to define the M principally injective. So here SEM is considered as a fully M cyclic submodule of M only. So if any homomorphism from this SEM to N can be extended from M to N, then N is called M principally injective. So here, if N is replaced by M itself, then any homomorphism from M cyclic submodule to M can be extended from M to M such that this diagram is commutes. We get G composition I is same as F, then we have to say M is semi-injective module. So the module where we are interested needs only fully invariant M cyclic submodule, which extends the notion of M principally injective and semi-injective module to the FI-M principally injective and FI semi-injective module. So here, now in this definition, we have to consider SM as a fully invariant M cyclic submodule of this module M. And here I is the inclusion map. So if every homomorphism F from this fully invariant M cyclic submodule SM to N can be extended to homomorphism G from M to N such that this diagram is commutative, G composition I is F, then we have to say N is FI M principally injective. And if N can be replaced by M, then we call M as a FI semi-injective module. And any ring R is called FI self-principally injective if R over R is FI R principally injective. So there are many examples. Every simple module, semi-simple module, quasi-injective module, semi-injective modules, and FI semi-principally injective rings, and their direct summand. All are FI semi-injective modules. And next example here we have to consider Z be the ring of integer, and N is Z4, which is denoted Z modulo 4Z, and M is considered Z6, is denoted Z by 6Z. Easily we verify N and M are the Z module, and we can say, we can check easily here, N is FI M principally injective and M is FI N principally injective, but Z is not Z principally injective modules over Z. Now, next example, here we have to consider, let R be the ring of upper triangular matrix like this here over the field F, and sorry, and M module is considered as the first row is non-zero and other row is 0 with the element of F field, and NR is here right corner down element only. So easily verify NR is FI M principally injective, but not M injective module, because here M cyclic submodule is 0 and M itself. But in case of submodule, there are one F is also a submodule, forms a submodule, but map from here to N cannot be extended to M to F. Okay, so now we come to the first result, which contains our basic results of the FI semi-injective module. If M cyclic submodule N of a module M is FI M principally injective, then N is a direct summand of M. That is, we can say here every short exact sequence from 0 to N to M to M1 is splits. And next result, we can say next part is every direct summand of FI semi-injective module is FI semi-injective. That is, we can say here FI semi-injective module is closed under the direct summand. And this is also, this structure is closed under the finite direct sum and finite direct summand. And next part here, if finite direct sum of MI modules is FI semi-injective, then MI is FI MJ relatively principally injective. And next part, we can say every injective endomorphism of uniserial FI semi-injective module is an automorphism. We can say uniserial FI semi-injective module is Cohaffian, where Cohaffian is defined like every injective endomorphism is an isomorphism, just like, for example, Artinian rings. Artinian rings are module. These are forms Cohaffian modules. And next property is considered as a definition. If N is FI M principally injective, if and only if the composition of homomorphism MN to G, where G is the endomorphism of M, is exactly same as collection of all the homomorphism from MN, such that kernel of G is contained inside the kernel of F. So this is the definition of the FI M principally injective. This can be extended on EFI semi-injective module as a definition. So we construct a corollary here. Let M be a EFI semi-injective module and FG are the endomorphism, some endomorphism of M. Then F in belongs to SG, means belongs to the SG if and only if kernel G content inside the kernel M. Now next result is consider M and N is a right arm module where M is the duo, then M is N projective and every submodule of N is EFI M principally injective. If and only if N is EFI M principally injective and every fully invariant M cyclic submodule of M is N projective. So now for next we have to define the PP ring, where it is defined like if each principal right ideal is projective, then we call ring R is PP ring. So our next result characterize the projective modules in terms of the EFI semi-injective, EFI M principally injective. So the following statements are equivalent for a projective module M. Every homomorphic image of any EFI M principally injective module is EFI M principally injective. If and only if every homomorphic image of any M injective module is EFI M principally injective. If and only if every homomorphic image of any injective R module is EFI M principally injective. And if and only if every fully invariant M cyclic submodule of M is projective. So this is the things, and the next result is obtained by the remarks here. We have just stated above, if every fully invariant M cyclic submodule of a module M is, if every fully invariant M cyclic submodule of M is a direct summand of M, then M is EFI semi-injective. So hence we make a remark, if the endomorphism ring S of any module M is 1 Newman regular, then M would be EFI semi-injective module. So with the help of these remarks, we construct a statement here. If S is the 1 Newman regular ring, then every fully invariant M cyclic submodule of M is EFI M principally injective. This is the first part, but converse of first part is not necessarily true. So this is holds for the direct projective module. So direct projective module can be defined any epimorphism from M to the direct summand of M is splits. That is kernel of F is a direct summand of M. So we can state the converse part of first result is here is hidden. So I am speaking here. So if M is direct projective and every fully invariant M cyclic submodule of M is EFI M principally injective, then S is 1 Newman regular. That's all. So now we have to state here, characterize the commutative semi-simple ring. The commutativity used in only proof in the proof of 2 implies 3. So the following statements are equivalent for a commutative ring R. The direct sum of any 2 EFI semi-injective module is EFI semi-injective. If and only if every EFI semi-injective module is injective, if and only if R is semi-simple Artinian. So commutativity used in only proofing in the second implies third, not in all. So now next result is the equivalent statement. The following statements are equivalent for a quasi-projective EFI semi-injective module, where S is the endomorphism of M. So image of S is EFI M principally injective. If and only if image of S is a direct summand of M, if and only if image of S is M projective. So 1 implies 2 is obtained from our first result, and here these are the have some little work for proving. So next result is the statement is true. In this statement is holds for means these are equivalent for a duo module M, where S is the endomorphism of M. So first is M is EFI semi-injective module if and only if left annihilator of kernel of F is same as ideal generated by F, left ideal generated by F, for all the endomorphism F. If and only if kernel of G is contained inside kernel F, then ideal generated by F is contained inside ideal generated by G, for all the endomorphism FG. And if and only left annihilator of image of G intersection kernel of F is same as left annihilator image G plus left ideal generated by F. So
Have 4 minutes.
okay. So corollary based on this result is having here. This is characterizes Fi self-principally injective ring. So this result is true equivalent for the commutative ring R. We can state R is right Fi self-principally injective ring if and only if annihilator of X is same as ideal generated by X. Here no concept of left and right concept is considered because here we are considering the commutative ring R. So annihilator of Y is contained inside annihilator of X. Then this implies ideal generated by X is contained inside the ideal generated by Y. And if the annihilator of ideal generated by Y intersection annihilator of X is same as annihilator of ideal generated by Y plus the ideal generated by X. And next result is we have to characterize Fi semi-injective module in terms of the endomorphism rings and their images. Here, let M be the duo Fi semi-injective module and Fg is the sum endomorphism of M. So here, if Fm is embedded into Gm, then Sf, ideal generated by F, is homomorphic image of Sg, ideal generated by S. And here, next part is Fm means Gm is an image of Fm, then Sg can be embedded into Sg. So next part, we can also conclude here, if Fm is isomorphic to Gm, then we can say Sg is isomorphic to Sf. Okay. So corollary based on this one, let R be a commutative Fi self-principally injective ring. So for any element X, Y of R, YR means ideal generated by Y is embedded into ideal generated by X. Then ideal generated by Y is an image of ideal generated by X. And if ideal generated by X is an image of ideal generated by Y, then ideal generated by X can be embedded into ideal generated by Y. So we can consider same just like parallel to previous, XR is isomorphic to YR, then RX is also isomorphic to RY. So this is the last slide. So here these are our references which are used to work here. And thank you. Any question or comment?
I would like to thank Professor Patel for his knowledge talk. Is there any questions or comments? If you have a question, you can write your question through the question and answer section.
See you.
Seems that there is no questions. Thank you again, Professor Patel, for your
Thank you.